Imagine you are traveling through space at nearly the speed of light. Your heart beats normally, your watch ticks. Yet on Earth, decades pass for every year you experience. Time is not universal. It is relative. Before Einstein, everyone believed in absolute time, a cosmic metronome that ticks the same everywhere. But in 1905, a 26-year-old Swiss patent clerk showed that every clock has its own pace. Motion changes time. Light, which we take for granted, reveals this secret. No matter how fast we move, light always travels at the same speed, 300,000 kilometers per second. This forces the universe to adapt. Space and time become flexible. And suddenly, the question becomes real. Can time really stop? If these cosmic journeys fascinate you every night, don't forget to subscribe to our channel and like the video. This helps the video reach even more people. Thank you in advance. Ready? Then let's begin. Part 1. The foundations of time dilation and Einstein's revolution. When time loses its rhythm. Imagine you're sitting in a spacecraft, accelerating to nearly the speed of light. Your watch ticks normally, but on Earth, something extraordinary is happening. For every year you experience, decades pass on Earth. At 99.9% of light speed, a single day for you becomes 2 months on Earth. But what happens if you actually reach the speed of light? Does time stop completely? This question leads us to one of the most fascinating discoveries in human history. Time is not absolute. It doesn't tick the same everywhere. Before Einstein, everyone believed time was like a universal clock, running at the same pace for all people everywhere in the universe. Isaac Newton built his entire physics on this assumption. For him, time was an unchangeable constant, a cosmic metronome that never changes its beat. But in 1905, a 26-year-old patent clerk in Switzerland shattered this comfortable illusion forever. Albert Einstein was his name. His special theory of relativity revealed something shocking. Time is personal. Every observer carries their own clock with them, and these clocks can tick at different speeds, depending on how fast they're moving. This sounds like science fiction, but it's not theoretical abstraction. It's measurable, observable reality. It affects everything, from the GPS in your smartphone to the particles raining down on us from space. The story begins with light itself. In the late 1800s, physicists discovered something disturbing. James Clerk Maxwell's equations showed that light propagates at a specific speed, about 300,000 kilometers per second in a vacuum. But speed relative to what? When you throw a ball from a moving train, its speed adds to the train's speed. Yet experiments showed that light doesn't follow this rule. Whether you're moving toward a light source or away from it, you always measure the same speed of light. Always exactly 300,000 kilometers per second. The Michelson-Morley experiment of 1887 attempted to detect Earth's motion through the presumed ether. The ether that was supposed to carry light waves. They found nothing. Light moved in all directions at the same speed, regardless of Earth's motion through space. This null result created a crisis in physics. A crisis that only Einstein could resolve. His solution was radical. He accepted that the speed of light is constant for all observers, and let everything else adjust. If the speed of light must remain constant, then space and time themselves must be flexible. This leads directly to time dilation, the slowing of time for moving objects. The mathematics is beautifully simple, yet profoundly strange. The time dilation factor, called gamma, equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. When you're standing still, gamma equals 1. No time dilation. But as velocity increases, gamma grows larger. This means time passes more slowly for the moving observer. At 10% light speed, time slows by just 0.5%, barely noticeable. At 50% light speed, time runs about 13% slower. At 90% light speed, time passes less than half as fast. At 99% light speed, time slows by a factor of 7. And as you approach 100% of light speed, something extraordinary happens. Gamma approaches infinity. This is where our journey becomes truly spectacular. The closer you get to light speed, the more extreme time dilation becomes. At 99.9% light speed, time slows by a factor of 22. At 99.99%, it's 71. Add more nines, and the factor grows without limit. At exactly light speed, the equation breaks. Gamma becomes infinite. This suggests that time stops completely. But here's the crucial point that's often misunderstood. From your perspective in the speeding spacecraft, time flows normally. Your watch ticks at 1 second per second. Your thoughts flow at normal speed. Your heart beats its usual 70 times per minute. Time dilation is only visible to external observers watching you zip past. This reciprocal nature of time dilation seems paradoxical. If you see Earth's clocks running slow as you speed away, and Earth sees your clocks running slow, who's right? The answer is both and neither. In special relativity, there's no absolute reference frame. Motion is relative, and so is time dilation. The asymmetry only appears when someone changes reference frames. Acceleration or deceleration breaks the symmetry. But what does this mean concretely? Imagine you could actually travel at 99% light speed. 1 year in the spacecraft would be 7 years on Earth. Your friends would age while you stay young. Your children would grow into adults while you barely age. Is this just theory? No. Real experiments have confirmed these predictions with breathtaking accuracy. In 1971, physicists Haffel and Keating flew atomic clocks on commercial airliners around the world. When they compared these two reference clocks on the ground, the flying clocks showed the predicted time dilation. They had aged slightly less than the stationary clocks. The difference was tiny, just nanoseconds, but measurable and exactly what Einstein had predicted. Particle accelerators provide even more dramatic confirmations. In CERN's Large Hadron Collider, protons are accelerated to 99.99% light speed. At this velocity, time dilation is so extreme that unstable particles that should decay in microseconds survive much longer. From our perspective, they travel meters instead of millimeters before decaying. Cosmic rays offer a natural demonstration. Muons are created when cosmic rays strike the upper atmosphere about 15 kilometers up. Muons have a half-life of just 2.2 microseconds. They shouldn't survive the journey to Earth's surface, even at nearly light speed. Yet we detect them in abundance at sea level. Why? Time dilation. From our perspective, their clocks run slow, giving them time to reach the ground. From the muon's perspective, length contraction makes the atmosphere thinner, reducing the distance it needs to travel. To perspectives, same reality. GPS satellites must account for time dilation to remain accurate. These satellites orbit Earth at about 14,000 kilometers per hour, fast enough that special relativistic time dilation slows their clocks by about 7 microseconds per day. Combined with gravitational time dilation, GPS clocks must be corrected by 38 microseconds daily. Without these relativistic corrections, GPS would accumulate errors of over 11 kilometers per day. Your smartphone navigates you correctly only because Einstein's theory is taken into account every moment. Every time you enter an address, you're confirming that time is relative. But what about photons, the particles of light that actually travel at light speed? Here it gets philosophically profound. According to special relativity, photons experience no time at all. From a photon's perspective, emission and absorption happen simultaneously, regardless of the distance traveled. A photon emitted by a star in the Andromeda galaxy, traveling for 2.5 million years from our perspective, experiences its entire journey in zero time. This leads us to one of the deepest mysteries in physics. What is the universe like from a photon's perspective? If time truly stops at light speed, then every photon exists in an eternal now, a timeless state where its entire journey from creation to absorption happens instantaneously. This isn't just philosophical speculation. It's a direct consequence of Einstein's equations. Think about the light entering your eyes right now. Some of it came from your screen, traveling for mere nanoseconds, but the ambient light bouncing around your room might contain photons that have been journeying for billions of years. The sunlight streaming through your window left the sun's surface 8 minutes ago, but the energy it carries was generated in the solar core hundreds of thousands of years ago. It slowly worked its way to the surface. From our perspective, these photons have vastly different ages and histories. But from the photon's perspective, if such a thing even makes sense, all journeys are identical. Zero duration. A photon traveling from the Big Bang to your eye experiences no time whatsoever. In its reference frame, the universe has zero thickness in the direction of travel. Its entire existence is compressed into a single, timeless moment. This raises profound questions about the nature of experience and consciousness. Can something that experiences no time exist in any meaningful sense? The impossibility of reaching light speed for massive objects isn't just a practical limitation. It's built into the fabric of space-time. As we've seen, the time dilation factor approaches infinity as velocity approaches light speed. This means it would take infinite energy to accelerate any mass to light speed. The universe has a built-in protection against massive objects reaching this ultimate speed limit. But why is this limit exactly what it is? Why 300,000 kilometers per second and not some other value? The answer lies deeper than you might expect. Light speed isn't really about light. It's the fundamental rate at which cause and effect can propagate through space-time. It's the speed of causality itself, the maximum rate at which information can travel. Light just happens to travel at this speed because photons are massless. The value of light speed emerges from two fundamental properties of empty space: the electric permittivity and magnetic permeability of the vacuum. These aren't arbitrary numbers. They seem to be woven into the structure of spacetime itself. In a very real sense, light speed is the conversion factor between space and time. It tells us how to translate between the two in our four-dimensional universe. Recent experiments have pushed our understanding of time dilation to new extremes. The Alpha experiment at CERN has trapped antihydrogen atoms and studied their properties, while these antimatter atoms move slowly compared to light speed. The precision of modern measurements allows scientists to test whether antimatter experiences time dilation identically to matter. So far, it does. Gravitational wave detectors like LIGO and Virgo have observed black hole mergers. Their objects spiral together at significant fractions of light speed in their final moments. The gravitational waves themselves propagate at exactly light speed. This confirms that gravity's influence travels at the same cosmic speed limit as electromagnetic waves. When two black holes merge, the final orbits see them moving at over half light speed. They experience extreme time dilation encoded in the gravitational wave signal. The twin paradox remains one of the most discussed aspects of relativistic time dilation. One twin stays on Earth, while the other travels to a distant star at nearly light speed. When the traveling twin returns, they've aged less than their Earth-bound sibling. This isn't a paradox once you understand that the traveling twin changed reference frames during their journey. They accelerated, turned around, and decelerated. This breaks the symmetry between the twins. Real-world examples of differential aging exist all around us. Astronauts on the International Space Station age slightly slower than people on Earth due to their orbital velocity. Scott Kelly spent 340 days in space, while his identical twin Mark stayed on Earth. Scott aged about 5 milliseconds less than Mark, a tiny but real effect of time dilation. But let's push further toward light speed. At 99.999% light speed, time dilation becomes so extreme that a journey to the center of our galaxy, 26,000 light-years away, would take just 52 years from the traveler's perspective. The entire observable universe could be crossed in a human lifetime if we could approach light speed closely enough. This creates a strange situation. The universe becomes traversable for the traveler, but at a terrible cost. Everyone and everything they knew on Earth would be long dead upon their return. Time dilation doesn't let you travel into the past, but it does let you travel into the future. A one-way journey from which there's no return to your original time. Quantum mechanics adds another layer of mystery to our story. While special relativity deals with the macroscopic world, quantum field theory describes particles and forces at the smallest scales. In this framework, virtual particles constantly pop into existence and annihilate, borrowing energy from the vacuum 4 times so brief they don't violate conservation laws. Do these virtual particles experience time? If they travel at light speed during their brief existence, are they timeless, like photons? The Unruh effect predicts that accelerating observers see empty space filled with a warm bath of particles. From the perspective of an accelerating observer approaching light speed, the vacuum itself would appear to heat up. Eventually, it would reach infinite temperature at light speed. This suggests that approaching light speed isn't just difficult. It's accompanied by increasingly exotic physical phenomena. String theory and other attempts at quantum gravity suggest that space-time itself might break down at the smallest scales. The Planck time, about 10 to the power minus 43 seconds, might represent the smallest meaningful unit of time. If so, then the smooth time dilation we calculate might become granular at extreme speeds, though this regime is far beyond current experimental reach. Recent proposals for detecting high-energy cosmic neutrinos rely on understanding time dilation at extreme energies. The IceCube detector in Antarctica has observed neutrinos with energies suggesting they're traveling at 99.99999% light speed or faster. At these speeds, time dilation is so extreme that neutrinos experience mere seconds while traversing billions of light-years from our perspective. To truly understand what happens to time at light speed, we need to think geometrically. Einstein's teacher Hermann Minkowski showed that special relativity is best understood by combining space and time into a 4-dimensional spacetime. In this geometric view, the mystery of time dilation becomes as clear as understanding why a tilted ladder appears shorter when viewed from the side. What we call time dilation is actually a rotation in four-dimensional space-time. Imagine space-time as a vast four-dimensional fabric. Every event, from the birth of a star to your heartbeat right now, has coordinates in both space and time. You're not just located somewhere, you're located somewhen. Your entire life traces a path through this four-dimensional space, called a world line. And here's the key insight. Everyone's world line has the same four-dimensional length between birth and death. But that length can be distributed differently between space and time. Think of it this way. You're always moving through space-time at exactly light speed. When you're sitting still in space, all your motion is through time. You're traveling into the future at maximum speed, 1 second per second. But when you move through space, some of that motion gets redirected. The faster you move through space, the slower you move through time. At light speed, all your motion would be through space, with none left for time. This geometric view explains why nothing can exceed light speed. You can't go faster through space-time than you're already going. Light speed is your total constant velocity through the four dimensions. Asking why we can't go faster than light is like asking why we can't go north of the North Pole. The geometry simply doesn't allow it. Have you made it this far? Then it's time to dive deeper into the mystery. Because what we've seen so far is just the beginning. The real paradoxes, cosmic phenomena, and existential questions still await us. What would it feel like to actually accelerate to light speed? What would you see? What would happen to your body? The answers will surprise you. They'll completely change your conception of what time is, and they'll show why the universe protects its speed limit so strictly. The journey has only just begun. Part 2. Experimental evidence and real-world applications. When theory becomes reality. The beauty of physics lies not in elegant equations alone. It lies in the moment when theory meets reality. When mathematics carved on paper transforms into measurable truth. Einstein's time dilation wasn't just a thought experiment, it was a testable prediction. And every single test, from basement laboratories to the edges of the cosmos, has confirmed it with breathtaking precision. Let's begin with one of the most elegant experiments ever conducted. The year was 1971. Two physicists, Joseph Haffel and Richard Keating, had a bold idea. They would take atomic clocks, the most precise timekeeping devices humanity had ever created, and fly them around the world. Not in specialized aircraft, but on regular commercial flights, flying east, then west, then comparing them to identical clocks that never left the ground. The prediction was clear. The flying clocks should age differently than the stationary ones. Not by hours or minutes, by mere nanoseconds. 1 nanosecond is 1/1000th of a second, a time interval so brief that light travels just 30 centimeters. Yet even this microscopic difference would prove Einstein right or wrong. The results were stunning. The eastward flying clocks lost 59 nanoseconds compared to the ground clocks. The westward flying clocks gained 273 nanoseconds. Both results matched Einstein's predictions within experimental error. Think about what this means. By simply flying on commercial airliners at cruising speed, moving at just a fraction of 1% of light speed, time itself measurably changed. But nanoseconds seem abstract. Let's make it concrete. Imagine you're a flight attendant who's spent 20 years flying international routes. You've circled the globe thousands of times. The cumulative effect of all that high-speed travel means you've aged about 100 microseconds less than if you'd stayed on the ground, 1/10 of a millisecond younger. Your body contains 1/10 of a millisecond less entropy, 1/10 of a millisecond fewer cell divisions. Now shift your attention to particle accelerators. These are humanity's most powerful microscopes, smashing particles together at nearly light speed to reveal the fundamental structure of matter. But they're also time machines. Every particle racing around these rings experiences time dilation so extreme it defies everyday intuition. At Fermilab's Tevatron, which operated until 2011, protons were accelerated to 99.9995% light speed. At these velocities, the time dilation factor exceeded 1000. Imagine that. 1000 seconds in the outside world equals 1 second for the proton. Unstable particles that should decay in nanoseconds survived for microseconds from our perspective. They traveled hundreds of meters instead of fractions of a millimeter before decaying. Every single decay curve matched relativistic predictions perfectly. Not approximately, not roughly, perfectly. The equations Einstein wrote in 1905, working with nothing but thought experiments and mathematical consistency, predicted the behavior of particles in accelerators that wouldn't be built for another 70 years. CERN's Large Hadron Collider pushes even further. This 27-kilometer ring beneath the French-Swiss border accelerates protons to 99.99991% light speed, just 3 meters per second shy of light itself. At this velocity, the time dilation factor reaches 7,460. What we observe as a microsecond of elapsed time is just 134 nanoseconds for the proton. The LHC is essentially a time machine, showing us how physics works when time nearly stops. But here's something even more profound. Despite humanity's most powerful machines, despite energies that recreate conditions from the first microseconds after the Big Bang, we cannot push particles those final 3 meters per second to true light speed. Each additional decimal place of precision toward the speed of light requires exponentially more energy. The universe's speed limit isn't just a suggestion. It's an absolute barrier that becomes infinitely strong as we approach it. You can spend all the energy in the solar system and still fall short. The mathematics is unforgiving. The physics is absolute. Cosmic rays provide natural experiments at energies beyond any accelerator. The Pierre Auger Observatory in Argentina sprawls across 3,000 square kilometers of desert, detecting particles from space with energies that dwarf anything humans can create. Some of these cosmic bullets carry energies exceeding 10 to the 20th electron volts. That's the energy of a baseball pitched at 90 kilometers per hour, concentrated in a single subatomic particle. These cosmic ray particles travel so close to light speed that crossing our galaxy takes mere seconds from their perspective. Yet precise timing measurements show they still fall short of true light speed. They still experience some passage of time, however infinitesimal. One particular cosmic ray, detected in 1991, nicknamed the "Oh my God" particle, had energy equivalent to a tennis ball traveling at 100 kilometers per hour. From our perspective, it had been traveling for millions of years. From its perspective, perhaps minutes, perhaps seconds, but not zero, never zero. The universe forbids it. The GZK cutoff provides a cosmic confirmation of extreme time dilation. Ultra-high energy protons interact with cosmic microwave background photons, losing energy through pion production. This creates a maximum distance from which we can detect the highest energy cosmic rays, about 100 million light-years. From the proton's perspective, the cosmic microwave background is blue shifted to gamma-ray energies. Imagine standing still while every photon around you transforms into a lethal radiation beam. This cosmic speed trap confirms our understanding of how time dilation affects particle interactions across the universe. Pulsar observations offer another window into relativistic time. The double pulsar system PSRJ 0737-3039 consists of two neutron stars orbiting each other every 2.4 hours. Their orbital velocity reaches 1 million kilometers per hour, significant enough for measurable time dilation. These pulsars act as cosmic clocks, each sending radio pulses with millisecond precision. After 20 years of observations, astronomers have measured how orbital motion affects each clock. The results: they confirm time dilation to better than 1 part in 10,000. Imagine measuring something to that precision. It's like measuring the distance from New York to Los Angeles and being accurate to within 400 meters. Gamma-ray bursts provide the most extreme astrophysical tests. These cosmic explosions, caused by collapsing massive stars or merging neutron stars, accelerate particles to Lorentz factors exceeding 1000. Time dilation so extreme that 1 second in the particle frame equals over 15 minutes in hours. The afterglow evolution of gamma-ray bursts follows precise patterns predicted by special relativity. Every observation, from dozens of different bursts across billions of light-years, confirms Einstein's equations. The cosmic microwave background itself demonstrates time dilation on the largest scales. This ancient light has been traveling for 13.8 billion years, redshifted from brilliant white to invisible microwaves. But the CMB also shows us the universe when time itself was different. In the early universe, the density of energy affected the rate of cosmic expansion and thus the flow of time itself on cosmic scales. Gravitational wave observations add a new dimension to testing extreme physics. When LIGO detected merging black holes in 2015, the final orbits involved velocities exceeding half light speed. The gravitational waves encoded information about time dilation in the strong field regime where special and general relativistic effects combine. Every merger detected since, over 90 events and counting, has matched predictions. The universe speaks in gravitational waves, and it speaks the language Einstein taught us. Laboratory experiments with stored ions push precision to new extremes. At the GSI Helmholtz Center in Germany, lithium ions accelerated to 34% light speed show time dilation in their electron transitions. Spectral lines are shifted exactly as relativity predicts. These experiments can measure time dilation to parts per billion, finding perfect agreement with theory. The Global Positioning System provides an everyday confirmation that most people don't realize. GPS satellites orbit at 14,000 kilometers per hour, experiencing time dilation of about 7 microseconds per day. This seems tiny, but GPS requires nanosecond precision. Without relativistic corrections, GPS errors would accumulate at 11 kilometers per day. Every time your phone finds your location, every time you navigate to an unfamiliar address, every time a delivery driver finds your house, you're confirming that time really does slow with motion. The system works because engineers programmed Einstein's equations into every satellite. Atomic clock experiments have become extraordinarily sophisticated. In 2010, researchers at NIST compared optical atomic clocks at different heights, measuring gravitational time dilation from just 33 centimeters of elevation difference. While this is gravitational rather than motional time dilation, it demonstrates our ability to measure time's flow with 18-digit precision, accurate enough to detect walking speed velocities if applied to motion. The IV's Stilwell experiment, first performed in 1938 and refined many times since, directly measures time dilation through the transverse Doppler effect. When atoms move perpendicular to the line of sight, classical physics predicts no frequency shift, but relativity predicts a redshift due to time dilation. Modern versions achieve precision of parts per billion, always confirming Einstein's predictions. Moyne storage rings provide controlled tests of time dilation. At Brookhaven's G-2 experiment, muons circled a magnetic storage ring at 99.94% light speed. Their lifetime dilated by a factor of 29.3. Exactly as predicted. The experiment also revealed subtle effects from Thomas precession, a relativistic correction to spinning particles in circular orbits. Space missions offer unique opportunities to test time dilation. The gravity probe, an experiment in 1976, carried a hydrogen maser clock on a rocket to 10,000 kilometers altitude. Comparing its frequency to ground clocks revealed both gravitational and motional time dilation, matching predictions to 70 parts per million. Future missions with improved clocks could test relativity to unprecedented precision. But let's bring this back to human scale. What does all this mean for you? Right now, as you read these words, you're experiencing time at a certain rate. If you stood up and walked across the room, you would experience time dilation. Infinitesimal, yes. Unmeasurable by any clock you own, yes. But real. The faster you move, the slower time passes for you compared to someone standing still. This isn't philosophy, it's physics. It's been measured. It's been confirmed thousands of times in thousands of ways. Every GPS satellite, every particle accelerator, every cosmic ray detector, every atomic clock experiment screams the same truth. Time is not absolute. Consider the International Space Station. Astronauts live there for months at a time, orbiting Earth at 28,000 kilometers per hour. Over a 6-month mission, an astronaut ages about 7 milliseconds less than people on Earth. 0.007 of a second. Scott Kelly holds the American record, spending 340 days in space. His identical twin brother Mark stayed on Earth. When Scott returned, he was younger than Mark. Not subjectively, not metaphorically, physically, measurably, scientifically younger by about 5 milliseconds. Their DNA showed differences. Their telomeres, the caps on chromosomes that shorten with age, showed different patterns. Time dilation isn't just about clocks. It's about biology. It's about aging. It's about life itself. Now imagine pushing this further. At 50% light speed, time runs 13% slower. A 10-year journey would be 11.5 years on Earth. You'd miss your child's entire elementary school years. At 90% light speed, time dilation becomes dramatic. A 5-year mission becomes 11 years on Earth. Your friends start careers, get married, have children while you're gone. At 99% light speed, the effect is stunning. 1 year in space equals 7 years on Earth. An astronaut leaving at age 30 would return at age 40 to find their 53-year-old twin greeting them. Their children would be teenagers. Their parents might be gone. At 99.9%, the numbers become almost surreal. Travel to the center of our galaxy and back, 26,000 light-years each way. From Earth's perspective, 52,000 years minimum. From the traveler's perspective, with sufficient speed, perhaps a lifetime, perhaps decades. You could witness cosmic distances in human timescales. The entire galaxy becomes traversable. But at what cost? Everyone you knew would be dust. Their children's children's children long dead. You would return to a civilization utterly transformed. to a world that barely remembers yours. Time dilation offers a strange form of time travel, not to the past that remains forbidden, but to the future, a one-way ticket to tomorrow. You cannot go home again, not to your time. The universe allows you to skip forward but never backward. This asymmetry, this arrow of time, seems built into the fabric of reality itself. Recent experiments have pushed the boundaries even further. Researchers have measured time dilation in individual ions, single atoms held in electromagnetic traps. They've observed how motion affects quantum states, how velocity changes energy levels, how time itself is woven into the quantum fabric of reality. The European Space Agency's CES mission, planned for the near future, will place ultra-precise atomic clocks on the International Space Station. These clocks will test relativity to 1 part in a billion. That's 18 decimal places of precision. At that level, we might detect deviations from Einstein's theory that point toward new physics. Or we might confirm, once again, that Einstein was right. Some experiments test time dilation using light itself. When you accelerate atoms and measure their emitted light, the frequency shifts. This Doppler effect has both a classical component, like the changing pitch of a siren, and a relativistic component from time dilation. By carefully measuring light from moving atoms, physicists can separate these effects and test time dilation directly. Every test, without exception, has confirmed Einstein's predictions. Not roughly, not approximately, precisely. The universe speaks mathematics, and time dilation is part of its grammar. But experiments don't just confirm theory. They raise new questions. If time dilation is real, what does it mean for causality? For the order of events? For the nature of existence itself? These questions lead us deeper into the mystery. The experiments have proven time dilation exists. They've measured it with exquisite precision. They've shown it affects everything from GPS satellites to cosmic rays, from atomic clocks to human aging. But measuring something and understanding it are different things. We know time dilation happens. We can calculate it. We can predict it. But why does it happen? What is time that it can slow down? How can something as fundamental as temporal flow be variable? These questions take us beyond experiment into the realm of geometry, mathematics, and philosophy. They force us to reconceive what time actually is. And that journey, from measurement to meaning, from data to understanding, is where the real mystery begins. Have you ever wondered what time actually feels like to move at relativistic speeds? The experiments show us the numbers. They prove the effect is real. But what would you experience? What would the universe look like? How would reality transform as you approached the cosmic speed limit? The answers lie ahead in a geometric vision of space-time that will change how you see the universe forever. Part 3: Space-Time, Geometry, and Philosophical Paradoxes. When reality bends in 4 dimensions, we've seen the experiments. We've measured time dilation with atomic precision. But measurement alone doesn't bring understanding. To truly grasp what happens to time at light speed, we must think in a way that defies human intuition. We must learn to see the universe not as 3-dimensional space changing through time, but as a single 4-dimensional entity where time and space are woven together into something called space-time. This insight came from Hermann Minkowski, Einstein's former mathematics professor. In 1908, just 3 years after Einstein published Special Relativity, Minkowski made a stunning declaration. Space by itself and time by itself are doomed to fade away into mere shadows. Only a union of the two will preserve reality. What did he mean? Imagine you're describing an event. You don't just say where it happened, you say when. A concert at the opera house means nothing without a date and time. Every event in the universe has 4 coordinates. 3 for position in space, 1 for position in time. These 4 numbers locate the event in 4-dimensional space-time. Your entire life, from birth to death, is a path through this 4-dimensional landscape. A world line connecting your first moment to your last. Now here's the revolutionary insight. Everyone's world line through space-time has the same total length between birth and death. But that length can be divided differently between space and time. Imagine you have 100 units of motion through space-time. If you're sitting still in space, all 100 units go into motion through time. You're traveling into the future at maximum rate, 1 second per second. But when you start moving through space, some of those units get redirected. Maybe 90 go to time, 10 to space. The faster you move through space, the more units shift. At 50% light speed, perhaps 50 units go to time, 50 to space. At light speed, all 100 units would go into motion through space. 0 left for time. This is why time stops at light speed. Not because some mysterious force slows clocks, but because all your motion through space-time has been redirected into spatial motion. You're always moving through space-time at exactly light speed. Always. Right now, sitting still, you're moving through time at light speed. When you move through space, you're just rotating your velocity vector in 4 dimensions, trading temporal motion for spatial motion. This geometric view makes everything clear. Time dilation isn't a mysterious effect. It's simply the consequence of rotation in 4-dimensional space-time. Just as a ladder looks shorter when tilted, your temporal progression looks slower when you're moving through space. The mathematics of this rotation is encoded in the Lorentz transformation. Just as rotating an object in 3 dimensions mixes its length, width, and height, moving through space-time mixes space and time coordinates. But there's a crucial difference. Ordinary rotations use circular functions, sine and cosine. Space-time rotations use hyperbolic functions. This is why space-time geometry is called Minkowskian, or hyperbolic, rather than Euclidean. The minus sign in the space-time interval equation, the difference between space and time coordinates, creates this hyperbolic character. Think about what this means for simultaneity. In Newton's universe, everyone agreed on what now meant across the cosmos. If 2 supernovas exploded simultaneously, they exploded simultaneously for everyone, everywhere. But in Einstein's universe, simultaneity is relative. Events that are simultaneous for one observer happen at different times for another observer moving at a different velocity. Consider a thought experiment. You're standing on a train platform as a high-speed train passes. Lightning strikes both ends of the train simultaneously in your reference frame. You see the flashes at the same moment because you're equidistant from both ends. But for someone on the train, moving toward one strike and away from the other, the strikes aren't simultaneous. The strike at the front happens first, from their perspective. Neither perspective is wrong. Simultaneity simply isn't absolute. And this relativity of simultaneity becomes extreme as speeds approach light speed. At 99% light speed, events you see as hours apart might appear simultaneous to the moving observer at light speed. All of space-time along the direction of motion collapses to a single moment. The light cone structure provides the ultimate framework for understanding causality. At every point in space-time, Imagine two cones touching at their tips. The future light cone contains all events that this point can influence. The past light cone contains all events that could have influenced this point. Everything else is in the elsewhere, events that cannot be causally connected without faster-than-light travel. For massive objects, world lines must always stay within the light cones, moving from past to future. But photons travel along the light cones themselves, on the boundary between time-like and space-like separation. This boundary existence is why photons experience no time. They're always on the edge between cause and effect, between past and future. This geometric understanding reveals something profound. The universe isn't a three-dimensional space that changes through time. It's a four-dimensional block where past, present, and future all exist simultaneously. We temporal beings experience slices of this block universe, one moment at a time. But from a higher perspective, from outside time, all of history exists at once. Your birth, this moment, your death, all equally real, all equally present in the eternal structure of space-time. Does this mean the future already exists? That free will is an illusion? These questions have haunted philosophers since Minkowski. The block universe interpretation suggests that time doesn't flow. We simply move along our world lines, experiencing successive events. But quantum mechanics introduces uncertainty that might preserve some form of agency. The intersection of relativistic determinism and quantum indeterminacy remains one of philosophy's deepest puzzles. Now let's confront the paradoxes. These aren't just mathematical curiosities. They reveal fundamental truths about time, causality, and existence itself. The twin paradox remains the most discussed. One twin stays on Earth. The other travels to a distant star at 99% light speed. The journey takes 10 years from Earth's perspective. But for the traveling twin, experiencing time dilation by a factor of 7, only 1.5 years pass. When they reunite, the traveling twin is younger. Not subjectively, physically, biologically, measurably younger. But wait, isn't motion relative? From the traveling twin's perspective, Earth moved away at 99% light speed. Shouldn't Earth's clocks run slow? Shouldn't the Earth twin be younger? This seems like a paradox. Two contradictory conclusions from the same situation. The resolution lies in acceleration. The traveling twin changed reference frames during their journey. They accelerated to leave Earth, decelerated at the distant star, accelerated to return, and decelerated at Earth. These accelerations break the symmetry between the twins. The traveling twin's path through space-time has a different character than the stationary twin's path. In geometric terms, the traveling twin's world line is shorter. Less proper time elapses along a bent path than a straight one. This isn't symmetric because acceleration involves a preferred reference frame. Real-world examples exist. Scott Kelly spent 340 days on the International Space Station. His identical twin Mark stayed on Earth. When Scott returned, he was about 5 milliseconds younger than Mark. Not much, but real, measurable. The asymmetry came from Scott's acceleration and deceleration, his changes of reference frame. But let's push this further. Imagine the traveling twin accelerates to 99.99% light speed. Time dilation factor of 70. A journey to a star 70 light-years away takes 70 years from Earth's perspective. But for the traveler, just 1 year. They age 1 year while Earth ages 70. They could visit their own great-grandchildren. This creates a strange reality. Time dilation doesn't let you travel into the past. but it does let you skip forward in time. You can travel to Earth's future, witnessing events decades or centuries hence. But you can never go back. Everyone you knew is gone. Your world has vanished into history. This one-way nature of time travel seems built into the structure of space-time itself. The relativity of simultaneity creates even stranger scenarios. Imagine a spacecraft traveling at 99% light speed past Earth just as two supernovas explode, one ahead and one behind Earth's position. From Earth's perspective, they explode simultaneously. But from the spacecraft's view, the forward supernova explodes first. Now add a second spacecraft traveling in the opposite direction. It sees the rear supernova explode first. 3 observers, 3 different orderings of events. As we approach light speed, these differences become extreme, challenging our notion of a universal now. If you're traveling at 99.99% light speed, events Earth sees as years apart might appear simultaneous to you. At exactly light speed, all of space-time in your direction of motion collapses to a single instant. The ladder paradox illustrates length contraction. A ladder 20 meters long moves at 90% light speed toward a garage 10 meters deep. Length contraction shrinks the ladder to less than 9 meters from the garage's perspective. It fits inside. But from the ladder's perspective, the garage is contracted to less than 5 meters. The ladder doesn't fit. Both perspectives are correct because simultaneity is relative. When the front of the ladder enters the garage isn't simultaneous with the back entering from different reference frames. The searchlight paradox offers another puzzle. Imagine a lighthouse whose beam sweeps across the sky. At sufficient distance, the spot of light on clouds moves faster than light speed. Does this violate relativity? No, because the spot isn't a physical object. It's a projection. No information or energy actually travels faster than light, but this paradox helps us understand why reaching light speed is impossible. It would require coordinating events across space faster than causality allows. Quantum mechanics adds new layers of paradox. The EPR paradox and quantum entanglement seem to violate light speed limits. Entangled particles correlate instantaneously regardless of separation. Measure one particle's spin and you instantly know the other's spin, even if it's on the other side of the galaxy. But careful analysis shows no information travels faster than light. The correlations are real but can't be used for communication. This suggests the universe allows instantaneous correlations while still protecting causality. A subtle distinction that took decades to understand. Does this mean quantum mechanics violates relativity? No. It means reality is stranger than either theory alone suggests. The quantum Zeno effect shows that frequent observation can freeze a quantum system's evolution. If time stops at light speed, would quantum systems be perpetually frozen? Would superposition never collapse? The intersection of quantum mechanics and relativistic time dilation remains one of physics' deepest mysteries. Consider consciousness itself. Our awareness seems intrinsically temporal. Thoughts flow, memories form, experiences unfold. William James called consciousness a stream, emphasizing its temporal nature. But if time stops at light speed, could consciousness exist? This isn't just about photons. It's about whether awareness itself requires duration or if some form of timeless consciousness is possible. Eastern philosophies have long spoken of timeless states of consciousness, the eternal now of meditation, the dissolution of temporal awareness in mystical experiences. While these are subjective experiences within time rather than truly timeless states, they hint at modes of awareness that transcend ordinary temporal flow. The physics of light speed gives unexpected support to these ancient insights about time's malleable nature. The ship of Theseus paradox becomes extreme at relativistic speeds. If you travel at near light speed, your atoms remain the same, while Earth's atoms are replaced multiple times through metabolism and repair. Which you is more continuous? The one whose atoms are preserved by time dilation, or the one whose patterns persist through atomic replacement? Identity itself becomes problematic when time flows at different rates. Death and immortality take on new meanings near light speed. A traveler approaching light speed arbitrarily closely could outlive the stars, watching the universe's entire future history unfold in what feels like a human lifetime. This isn't immortality in the traditional sense. The traveler still ages and dies in their own reference frame, but it's a kind of temporal transcendence, experiencing eons of cosmic time. The information paradox becomes acute at light speed. Information cannot travel faster than light. This is fundamental to causality. But if time stops at light speed, how can information be processed? A computer traveling at light speed would be frozen, unable to complete calculations. This suggests that consciousness, computation, and information processing are fundamentally incompatible with light speed travel. Consider the photon's journey from distant galaxies. Some photons we detect today have been traveling for over 13 billion years, carrying information about the early universe. From our perspective, they're ancient messengers. But from the photon's perspective, emission and detection are simultaneous. How can something convey information about the past if it experiences no time? This paradox touches on deep questions about the nature of information itself. The expansion of space adds another paradox. Galaxies can recede from us faster than light due to cosmic expansion. Space itself stretches, carrying galaxies apart. From our perspective, time dilation should affect these galaxies. But the expansion of space isn't motion through space, so special relativistic time dilation doesn't apply directly. Instead, cosmological time dilation stretches the duration of events we observe in distant galaxies. Black holes create the ultimate time paradox. As matter approaches the event horizon, gravitational time dilation approaches infinity. From outside, we never see anything cross the horizon. Time freezes at the boundary. Yet, from the falling object's perspective, crossing happens in finite time. This paradox connects to the black hole information problem and suggests that time's nature changes fundamentally in extreme gravity. The tachyon paradox explores what would happen if something could travel faster than light. Such particles would move backward in time from some reference frames, enabling grandfather paradoxes where effects precede causes. The universe seems to forbid tachyons, maintaining causality by enforcing the light speed limit. Every search for tachyons has failed, suggesting the universe really does protect its causal structure. Light speed isn't just a speed limit. It's a guardian of logical consistency. Wormholes, if they exist, would create closed time-like curves, paths through spacetime that loop back to their own past. But quantum effects seem to destabilize any wormhole that could create paradoxes. The universe appears to have what Hawking called a chronology protection agency, preventing paradoxical situations. Every attempt to create a time machine runs into this barrier. The cosmos forbids logical contradictions. Recent experiments with quantum optics have probed the nature of time for photons in unprecedented ways. Researchers have created elaborate setups where single photons travel through interferometers, with path lengths differing by many meters. Despite these different paths, the photon interferes with itself. suggesting it somehow experiences all paths simultaneously in its timeless journey. The Wheeler-Feynman absorber theory proposed an even stranger view. Photons might experience their entire journey from emission to absorption as a single event, with the future absorption affecting the past emission. While this interpretation remains controversial, it highlights how deeply mysterious the photon's timeless perspective remains. These paradoxes aren't problems to be solved. They're windows into the deep structure of reality. They show us that time isn't what we thought it was, that causality is more subtle than simple before and after, that existence itself takes forms we can barely comprehend, and they all point to the same conclusion. At light speed, time stops. Not metaphorically, literally. The equations don't lie. The experiments confirm it. But understanding what that means requires us to abandon our intuitions about time, about causality, about the nature of existence itself. We must learn to think in 4 dimensions, to see the universe not as it appears to our time-bound consciousness, but as it truly is, an eternal geometric structure where past, present, and future are equally real, equally present. And that realization, that shift in perspective, opens the door to even deeper mysteries. If space-time is a fixed 4-dimensional structure, what about the cosmic phenomena we observe? The black holes and quasars, the merging galaxies and expanding universe? How does time dilation manifest on these cosmic scales? What happens when gravity enters the equation, warping space-time itself? Those questions await us in the cosmic arena, where time and space dance at the edge of infinity. Part 4. The universe's speed limit and cosmic phenomena. When the cosmos tests Einstein's limits. Why 300,000 kilometers per second? Why not faster? Why not slower? This isn't arbitrary. The speed of light emerges from the fundamental structure of empty space itself. 2 properties define the vacuum: electric permittivity and magnetic permeability. These aren't random numbers plugged into equations. They're woven into the fabric of reality. Light speed isn't really about light. It's the speed of causality, the maximum rate at which cause and effect can propagate through space-time. Light travels at this speed because photons are massless. But the speed limit itself is deeper. It's the conversion factor between space and time, the universe's way of saying these 2 things are aspects of a single entity. Think of it like an exchange rate. How many meters equal 1 second? The answer is 300 million. That's what the speed of light tells us. Space and time are different currencies measuring the same underlying reality, and the exchange rate is fixed by the properties of the vacuum itself. The Higgs field adds another layer to this story. This invisible field permeates all of space, giving particles their mass. When particles move through the Higgs field, they experience resistance. The faster they go, the more resistance they feel. At relativistic speeds, this resistance becomes extreme. It's as if space itself thickens into cosmic molasses. This isn't just metaphor. The equations show it clearly. As velocity approaches light speed, the energy required to accelerate further increases without bound. You can pour in all the energy in the universe and still fall short. The final gap can never be closed for massive objects. Virtual particles in the quantum vacuum create additional friction. Empty space isn't really empty. It seethes with particle-antiparticle pairs popping in and out of existence. At extreme velocities, these quantum fluctuations create drag, another mechanism enforcing the speed limit. The universe uses every tool at its disposal to protect causality. Now let's venture into the cosmos. Here, Nature conducts experiments at energies and speeds we can barely imagine. In the center of our galaxy, a supermassive black hole lurks. Sagittarius, a star, 4,000,000 times the Sun's mass, compressed into a region smaller than Mercury's orbit. Stars orbit this monster at breathtaking speeds. The star S2 swings past the black hole every 16 years, reaching velocities of 5,000 kilometers per second. That's almost 2% of light speed. During its closest approach, S2 experiences measurable time dilation, about 1%. Time passes measurably slower for this star than for us watching from Earth. We've tracked S2 for over 20 years with the gravity instrument on the Very Large Telescope. The observations are exquisite. We can see the star's light redshift as it plunges toward the black hole. Not just gravitational redshift from the intense gravity, but also Doppler shift from its velocity, modified by time dilation. Einstein's equations predict every detail. Every measurement confirms the prediction. Imagine standing on a planet orbiting S2 during its closest approach. You'd see the distant universe speed up slightly. Stars would evolve faster. Events would unfold in fast forward. Meanwhile, anyone watching you would see you in slow motion. Your clock's running slow. Your movements languid. Two perspectives, same reality. Quasar jets provide even more extreme laboratories. These cosmic fire hoses shoot plasma from supermassive black holes at 99% light speed or higher. The Quasar 3C279 displays knots of material that appear to move at 7 times light speed across the sky, an illusion created by time dilation and projection effects. The material is actually moving at about 99.8% light speed at a small angle to our line of sight. These jets maintain coherence over millions of light years despite their extreme velocities. From our perspective, particles in the jet age incredibly slowly, allowing unstable particles to travel vast distances. From the jet's perspective, the universe is length contracted, making intergalactic journeys seem much shorter. It's a cosmic demonstration of how approaching light speed warps both space and time. Binary millisecond pulsars showcase time dilation with clockwork precision. PSRJ 1909-3744 spins 339 times per second while orbiting a white dwarf companion. This system acts like a cosmic clock shop with multiple timekeepers moving at different velocities. Pulsar timing arrays have measured how orbital motion affects each clock, confirming relativistic time dilation to better than 1 part in a million. The precision here is staggering. Imagine measuring something so accurately that an error of 1 second would take 1,000,000 seconds over 11 days to accumulate. That's the level of precision modern radio astronomy achieves. And every measurement, every pulse, every timing residual confirms Einstein's century-old equations. Gamma-ray bursts are the universe's most violent explosions. When massive stars collapse or neutron stars merge, they create jets of material accelerated to Lorentz factors exceeding 1,000. At these speeds, time dilation is so extreme that 1 second in the particle frame equals over 15 minutes in hours. The afterglow evolution follows precise patterns predicted by special relativity. We've observed dozens of these cosmic cataclysms across billions of light years. Every single one behaves exactly as relativity predicts. The light curves, the spectral evolution, the timing of different wavelengths, all match the equations. Nature conducts these experiments at energies we can't recreate in laboratories, and nature speaks Einstein's language. Black holes create the ultimate time dilation. At the event horizon, time dilation becomes infinite from an outside observer's perspective. Watch something fall toward a black hole and you'll never see it cross. The object appears to slow down, redshift, and freeze at the horizon, its final moments stretched into eternity. Yet, from the falling object's perspective, nothing special happens at the horizon. You'd cross in finite time, experiencing the interior that outside observers can never witness. This creates a profound asymmetry. To observers, experiencing completely different realities. The information paradox emerges from this tension. Information falling into a black hole appears frozen at the horizon from outside perspectives, but the black hole eventually evaporates through Hawking radiation. What happens to that information? Does it vanish, violating quantum mechanics? Or does it somehow escape, violating general relativity? This puzzle has driven decades of research into quantum gravity. The merger of two black holes displays time dilation on cosmic scales. LIGO and Virgo have detected over 90 such events. In the final moments before merger, the black holes orbit at over half light speed. The gravitational waves themselves encode the time dilation of this dance. Each chirp in the signal carries information about velocities approaching the cosmic speed limit. When we analyze these signals, we're literally hearing time dilation, the stretching and compression of space-time translated into sound. It's Einstein's equations made audible. Cosmic strings, if they exist, would be one-dimensional defects in space-time moving at near light speed. These hypothetical objects would create gravitational lenses with unique signatures, double images with no distortion. The detection of cosmic strings would reveal how one-dimensional objects experience time at relativistic velocities, potentially confirming or challenging our understanding of time dilation. The cosmic neutrino background, relic neutrinos from the Big Bang, fills space with particles moving at nearly light speed. These ancient neutrinos have been traveling since the universe was 1 second old, experiencing extreme time dilation throughout cosmic history. When we eventually detect them directly, we'll be observing particles for which billions of years have passed, like moments. Active galactic nuclei show coordinated variations across vast distances. In some cases, different parts of the accretion disk brighten in sequence, as if a signal is propagating faster than light. The explanation involves time dilation and light travel delays, combining to create apparent superluminal coordination. These cosmic illusions teach us how time and causality interweave at extreme velocities. The universe's expansion adds another layer to cosmic time dilation. Distant galaxies recede from us at significant fractions of light speed due to cosmic expansion. Their time appears to run slow from our perspective. Supernova in distant galaxies evolve in slow motion. This cosmological time dilation is distinct from special relativistic effects, showing how space itself can affect time's flow. Imagine watching a supernova explosion in a galaxy 10 billion light-years away. The explosion that takes weeks to brighten and fade in its own reference frame appears to take months from our perspective. The light is stretched by cosmic expansion, but so is time itself. Each moment in that distant galaxy is dilated from our viewpoint. Magnetars, neutron stars with extreme magnetic fields, accelerate particles along field lines to near light speed. The magnetic field strength can exceed 10 to the 15th Gauss, creating conditions where quantum electrodynamics predicts vacuum birefringence and photon splitting. These exotic environments probe how electromagnetic fields behave when particles approach the speed of light. Recent observations with the Hubble Space Telescope have captured jets from young stars moving at relativistic speeds. These stellar nurseries show us star formation in action, with material ejected at velocities where time dilation becomes measurable. We're witnessing cosmic birth accelerated to near light speed. The Crab Nebula pulsar, spinning 30 times per second, creates a wind of particles moving at 99% light speed. This cosmic lighthouse has been observed for nearly 1,000 years since its parent star exploded in 1054. The nebula itself glows with synchrotron radiation from electrons spiraling in magnetic fields at relativistic speeds. Ultraluminous X-ray sources in distant galaxies display variability suggesting black holes accreting matter at near the theoretical limit. The material spirals inward at relativistic speeds, heating to millions of degrees and radiating X-rays. Time dilation affects how we observe these systems, stretching rapid flickering into slower variations. Every cosmic phenomenon we observe involving high velocities confirms time dilation. Not approximately, precisely. The universe is a vast laboratory testing Einstein's equations on scales, from subatomic particles to galactic jets. And every test, without exception, confirms that time is relative, that it slows with motion, that, at light speed, it stops. But these observations don't just confirm theory. They raise profound questions. If time dilation is universal, affecting everything from particles to galaxies, what does this mean for the nature of time itself? Is time an illusion, an emergent property, or something even stranger? These questions push us beyond physics into philosophy, consciousness, and the ultimate nature of reality itself. Part 5. Future Research and Existential Conclusions. The frontier between time and eternity. The next decades promise revolutionary insights into time's ultimate limits. New instruments will probe the boundary where time approaches zero. Theories will challenge Einstein's equations at extreme scales, and humanity will edge closer to understanding what it means to exist at the intersection of the temporal and the timeless. The Laser Interferometer space antenna, scheduled for launch in the 2030s, will detect gravitational waves from merging supermassive black holes. These cosmic collisions involve event horizons where time dilation becomes infinite. LISA's sensitivity will map space-time geometry near the ultimate limit where time stops. We'll observe dynamics in regions where seconds stretch to eternities. Quantum gravity theories suggest space-time itself breaks down at the Planck scale. Distances of 10 to the minus 35 meters, times of 10 to the minus 43 seconds. At these scales, the smooth time dilation of Einstein's relativity might become granular. Loop quantum gravity predicts discrete jumps in time rather than continuous flow. Time might not be infinitely divisible, but composed of fundamental units. Imagine time as a staircase rather than a ramp. Approaching light speed would involve stepping through discrete time states, each quantum leap bringing you closer to timelessness. If confirmed, this would revolutionize our understanding. Time wouldn't be smooth but pixelated at the smallest scales. The Event Horizon Telescope continues improving its resolution. Future observations might detect time dilation effects near event horizons in unprecedented detail. Watching matter spiral into black holes in real time could reveal how physics behaves when time approaches zero. We might observe quantum effects competing with gravitational time dilation, potentially discovering new physics at the boundary between quantum mechanics and general relativity. Quantum clock interferometry represents a frontier where measurement meets mystery. By putting quantum clocks in superposition of different velocities, physicists hope to observe quantum superpositions of different time dilations. This would probe whether time dilation obeys quantum mechanics, or if there's a fundamental conflict between quantum theory and relativity at extreme speeds. Imagine a clock that's simultaneously moving fast and slow, experiencing two different rates of time at once. What would such a measurement reveal? Could time itself be in superposition? The atomic clock ensemble in space will place ultra-precise atomic clocks on the International Space Station. Comparing these two ground clocks will test time dilation with unprecedented precision, potentially revealing tiny deviations from Einstein's predictions. Even parts per quintillion differences could indicate quantum corrections to relativity, a single-second error over the age of the universe. That's the precision we're approaching. Neutrino telescopes like IceCube detect particles with energies pushing theoretical limits. Some models suggest quantum gravity effects might allow particles to slightly exceed light speed at extreme energies. While no violations have been confirmed, each new high-energy neutrino tests the absolute nature of the cosmic speed limit. The search for Lorentz invariance violation continues with ever greater sensitivity. Some quantum gravity theories predict tiny variations in light speed depending on photon energy. Observations of gamma-ray bursts across billions of light-years could reveal if high-energy photons travel slightly faster or slower than low-energy ones. So far, light speed appears perfectly constant, but future observations might find surprises. Quantum entanglement experiments push toward macroscopic scales. If large objects can be entangled, we might observe how time dilation affects quantum correlations in ways current theory doesn't predict. This could reveal whether the timeless correlations of entanglement conflict with relativistic time dilation at observable scales. The holographic principle suggests our three-dimensional reality might be encoded on a two-dimensional surface. If true, time itself might be emergent from more fundamental timeless physics. Future experiments might detect the pixels of holographic spacetime, revealing that smooth time dilation is actually discrete at the smallest scales. Metamaterials with exotic optical properties allow simulating cosmic phenomena in laboratories. Researchers have created materials where light effectively travels faster than the speed of light, though information still can't exceed light speed. These superluminal materials might reveal new aspects of how time and causality relate when normal speed limits are circumvented. Time crystals, structures that repeat in time rather than space, challenge our understanding of temporal physics. Future experiments might create relativistic time crystals that combine periodic time behavior with extreme time dilation. This could reveal whether time's fundamental nature changes at relativistic speeds. Artificial intelligence might provide new insights into timeless physics. AI systems don't experience time the way biological consciousness does. As AI becomes more sophisticated, it might offer perspectives on what timeless information processing could mean, potentially illuminating the photon's perspective of reality. String theory predicts extra dimensions that might modify time dilation at extremely high energies. While these effects would be tiny, future particle accelerators or cosmic ray observations might detect signatures of extra dimensions through modified dispersion relations. Variations in how particles of different energies experience time dilation. But beyond experiments and theories lies a deeper truth. We stand at the intersection of two realms, the temporal and the timeless. We are beings who experience time made from particles governed by timeless laws. This duality defines our existence in ways we're only beginning to comprehend. Every photon that has ever existed experiences its entire journey in zero time. The sunlight warming your face left the sun 8 minutes ago from your perspective. But from the photon's view, departure, and arrival are one event. The cosmic microwave background radiation, traveling for 13.8 billion years to reach us, experiences its entire journey instantaneously. In the realm of light, all of cosmic history collapses into a single eternal moment. This timeless perspective reveals something extraordinary. Every point in space is connected to every other point through light's timeless journey. When you see a star, you're not just receiving old information. You're participating in a connection that, from light's perspective, is instantaneous across any distance. The universe isn't just connected by light, it's unified by it, in a timeless web that transcends our temporal experience. Consider what this means for your existence. You're made of atoms held together by electromagnetic forces. Virtual photons, timeless quantum messengers, mediate these forces. Every moment, timeless interactions sustain your physical form. You exist at the boundary between time and eternity. Your consciousness is fundamentally temporal. Every thought requires neurons firing in sequence. Every memory involves encoding experiences over time. Every decision projects into possible futures. The speed of light limit ensures these processes unfold in meaningful sequences. That causes lead to effects. That experiences accumulate into wisdom, yet you're also connected to the timeless realm. The light entering your eyes connects you instantaneously, from light's perspective, to everything you see. You are a bridge between two fundamentally different modes of existence. This duality extends throughout nature. Every atom dances between temporal electrons and timeless photons. Every chemical reaction involves massive particles moving through time while exchanging timeless force carriers. Modern physics hints this division might be even more fundamental. Some theories suggest time itself is emergent, that the timeless quantum realm is more basic. Time only appears for certain observers under certain conditions. We might be temporal islands in a fundamentally timeless reality, experiencing an illusion of flow in what is actually an eternal, unchanging whole. The implications for human existence are profound. We age and die in time, but the light we emit, the infrared radiation from our warm bodies, the radio waves from our technology, enters the timeless realm. In a sense, every moment of our existence is preserved in light that carries it into space, frozen in an eternal now that will outlast the stars. When you look at the night sky, you're seeing the universe's history laid out in space. But from light's perspective, all that history exists simultaneously. The Big Bang, the formation of galaxies, the birth of stars, the emergence of life, and the distant future when the last stars die, all coexist in the timeless realm of light. We temporal beings see slices of this eternal whole, experiencing it as a story unfolding through time. The search for meaning takes on new dimensions when we understand time's limits. We cannot achieve timelessness ourselves, but we participate in it every time we see or are seen. We're temporary patterns in a universe where time and timelessness interweave. Our brief temporal existence gains significance not despite its brevity, but because of it. We're the universe's way of experiencing time, just as light might be its way of transcending it. Science itself is our attempt to understand both realms. Through mathematics and observation, we temporal beings have discovered the timeless laws that govern reality. Equations like E equals mc squared are timeless truths we discovered at particular moments in time. We use our temporal consciousness to reach toward eternal principles, building bridges of understanding between the flowing and the fixed. As technology advances, we edge closer to light speed in our experiments, probing the boundary between time and timelessness. Each particle we accelerate toward the speed of light, each photon we detect from distant galaxies, each gravitational wave we observe from merging black holes teaches us more about this fundamental divide. We may never cross it ourselves, but we can approach it asymptotically, learning ever more about what lies on both sides. The question we began with, does time stop at light speed, has led us through the deepest mysteries of physics and philosophy. The answer is both yes and no. Yes, time stops for anything traveling at exactly light speed, but no massive object can ever reach that speed to experience it. This isn't a limitation, but a feature that makes our existence possible. We are beings of time, made from stardust, contemplating our place in a cosmos where time and timelessness coexist. Every atom in your body has experienced billions of years, yet the light reflecting from your eyes experiences no time at all. You are simultaneously ancient and instantaneous, temporal and connected to the timeless, finite yet touching the infinite. As you move forward from this moment, remember you exist at the intersection of two realms. You experience time's flow while being built from timeless laws. You age and change while participating in eternal patterns. You're separated from light's timeless perspective by an unbridgeable gap, yet connected to it every time you open your eyes. This is the profound gift of being human, to experience time while knowing about timelessness, to be finite while comprehending the infinite, to be mortal while touching the eternal through understanding. The universe has arranged itself so conscious beings like us must experience time to exist, while light, the very thing that allows us to see and know the cosmos, transcends time entirely. In this cosmic arrangement, we find not limitation but profound meaning. We are time's children, light's observers, and the universe's way of experiencing both the temporal and the eternal. And in understanding what happens when time stops at light speed, we discover not just physics, but poetry, not just equations, but existence itself. Even if we were to imagine pausing for a single moment in light's timeless universe, perhaps we would be embracing eternity. But we, the children of time, exist through the meanings we pour into seconds. We listen to the poem that light whispers to us in every sunset. We touch the ancient story of the universe in every starlight. Tonight, I invite you to sleep with the knowledge that we are at the very heart of this cosmic dance. Leave upon your pillow both the delicacy of our finitude and the splendor of our dreams that reach for the infinite. From that boundary where light defies time, I now whisper a soft good night. May your dreams be illuminated by the glimmers of timeless truths, carried on the rivers of time flowing towards tomorrow. Good night.